So let's try an example. I'm going to scooch this over just a little bit. If we need those further columns, I'll slide it back. Our first example is carbon. It's a nice easy one. And hopefully you can look at a periodic table and tell that carbon has 6 electrons because its atomic number is 6, and E negative is a symbol for 6. So using that chart I gave you in the notes right above this video and this off-ball diagram, we're going to start here, 1s. And how many electrons can that s orbital hold? It's only got one orientation, and each orientation holds 2, so we can put 2 electrons. And this superscript number is how we indicate how many electrons are in the 1s orbital. And then next, we go to 2s, and it's still an s orbital, so it can still hold 2. If we add up our superscripts, we have 2, 4, we need 6. So the next orbital is P. P can hold 6 because it has 3 orientations. Each of those can hold 2, but we only have 2 more electrons. So we will say 2. You should always be able to add up these superscripts and get your number of electrons. Let's also talk about that orbital configuration, what's going on in there. So we're just going to draw a line to represent each orientation. And in this s orbital, we have 2 electrons. One of them is going to spin up, and one of them is going to spin down. It doesn't really matter which one you draw first, and it doesn't really matter if it's up or down. It just matters that they're 2 different ones. And of course, that's because of the Pauli exclusion principle. So 2s2 is going to look just like that. Now 2p. P has 3 orientations, so we need to draw 3 lines. And Hund's rule tells us that they will be as many unpaired electrons as possible. So we have 2 electrons. We are not going to put them together. We will put them in separate orientations. So doing this only gets easier the more you practice. Let's do another example. Let's try magnesium. And if you look at the periodic table, magnesium has 12 electrons. So if we follow our off-ball diagram, the first 2 are going to go in 1s, because the s orbital can hold 2. And we know that's going to have 1 orbital, 1 orientation. So we'll go ahead and draw the line so we have enough space. Next it'll be 2s and 2. In fact, we can go ahead and do our configurations here. 1 up and 1 down. Let's talk about 2p. So we have 2, 4. This can hold 6, which will get us up to 10. So 1, 2, 3. 1 up and 1 down for each. And then after 2p, we go to 3s. If we add up, we've got 2, 4, and we have 10, so we have 2 more electrons. And that orbital is also full. So you can see that magnesium has no unpaired electrons at all, which will matter when we get to periodic trends in the next chapter. Let's do one more example. Let's do nickel. We have 28 electrons. Before we start, let's look at these orbital diagrams. You see what a 1s or what an s orbital looks like if it's full. It's got 1 up and 1 down. You see what a p orbital looks like if it's full. A d orbital, we'll have all the 5 lines full of up and down arrows. So you do not have to do the orbital configuration for any except the very last one you write. The one that may or may not be full, because those are your valence electrons. Those are the ones that cause all those properties we're talking about. So we can assume we know what a full orbital looks like. 1 up arrow, 1 down arrow for every orientation. So we're only going to worry about the very last one. Our nickel is going to start just like all the rest. 1s2, 2s2, and then 2p6. And then after 2p, you go down to 3s. And that's 2. So this is magnesium, this is 12. So we can keep going. After 3s, we go to the next arrow, and we start right here with 3p. And that's 3p6. And then we've got to make sure we're following the off-ball diagram, because otherwise we would go to 3d10 next, and that's not right. Next, according to this, is 4s. So 4s2. We know that this was 12. So this is 18. So this is 20. We have 8 more. After 4s, we go to 3d. The d orbital can hold up to 10, so we can put all 8 there. If we add all those numbers up, we get 28. So let's do our orbital configuration. It's d, so d has 5 orientations. 3, 4, 5. Hund's rule says as many unpaired electrons as possible. So we're going to put all of our up arrows in before we start pairing anybody up. Doesn't really matter if it's up or down. I just always start with the ups. So that's 5, 6, 7, 8. So you can see that nickel has 2 unpaired valence electrons and 3 pairs. And that'll be important in terms of its properties later. So let's do one more example like this. Let's do gold. Gold is Au. And it has 79 electrons, which is a lot. So we can start putting them in, following our little diagram. 1s2, 2s2. Even though this diagram makes it so that we don't have to memorize the order, you will do this enough that you will know it up to a certain point just from writing it over and over again. Like I can get to 3d10 always without having to look, because I know that order. So we go from 3d to 4p, 6. Let's count to make sure we don't go over. We have 10, and I'm going to make a little note so that I don't have to count it over again every time. 10, 12, 18, 20, 30, 36. So I'm going to make a little note here. 36. If you make these on your paper, do me a favor and try to erase them afterwards, okay? Because it'll confuse me when there's lots of extra numbers. So we have a lot more to go. After 4p, we follow that arrow, we have 5s. So 5s2. After 5s, 4d. So now I have 38, 48, still not there. After 4d, we go to 5p. And after 5p, we go to 6s. I'm going to squeeze this in. So we have 36, 38, 48, 54, and 56. So I'm going to add a little 56 right here to help me remember. After 6s, we're going to go to the next arrow, which is 4f. We haven't used f yet. F has 7 orientations, and each orientation can hold 2, so F can hold 14. Do we have 14 more electrons? Yeah. And then after 4F, we go to 5D, but I think we're going to run out of electrons here, so let's count. 56, so that's 70, we have 9 more. So 5D, 9. For our orbital configuration, we do our 3 lines. And we do 2, 3, 4, 5, 6, 7, 8, 9. Now you can see that this gets very tedious very quickly, because if you know it's going to have a ton of electrons, you know what all those lower orbitals are going to look like. It's always 1s2, 2s2, 2p6, 3s2, etc. So we have developed what we call noble gas configuration. It's a shorthand using the previous noble gas. The reason we pick noble gases is because they have full electron shells. They're kind of the ideal that everybody's going towards. So let's pick a simple one. Let's go with aluminum first. And I'll show you how to do these. Aluminum has 13 electrons. And if you look at your periodic table, the previous noble gas is neon. Now make sure it's not the case here, but don't tell me the closest noble gas, but the previous one, the one with less electrons. So to do this, we will put neon in brackets, and it's important that they're actually brackets, not parentheses. So this says the noble gas of neon. This is 10 electrons, and you can tell that because looking at the periodic table, you see that neon has 10 electrons. So you're telling me the first 10 electrons look just like neon. The next thing is to find out what period aluminum is in. Aluminum is in the third period. So you're always going to start in the s orbital of the highest energy level for that element. And we said that it's the same as their period. So aluminum, we are going to go onto our off-ball diagram and start right here with 3s. That can hold 2 electrons. So this gives us 10, 12. We have one more. Following our off-ball diagram, we go to 3p. So we have 3p1. You can still do your orbital configuration for that last one. We have 1 unpaired electron. Even if you only have an electron in one of those lines, you have to draw all 3 lines so that you are showing that there are 2 completely empty orientations. You have to show all of it. So you can see that this makes it a lot quicker and a lot easier when you get to those larger ones. You are going to need to be able to give me both, so make sure you practice both. But with the longer ones, I will pretty much always request noble gas, because otherwise it's just a waste of your time and mine, grade, and all of that. Let's do one more of these noble gases. Let's do uranium. It has 92 electrons. Now, if you look at your periodic table, uranium is in the F block, the parts we've brought out. Now, because it's in the F block, you know the last orbital is going to be an F. But it's sometimes hard to see which noble gas is in front of that. But just look at your atomic numbers. So what's the noble gas with an atomic number closest to 92? And if you look, hopefully you see it's right on. We're going to write Rn. And that has 86 electrons. And uranium is in period 7. So we're going to start at 7s. That gives us 88 electrons. Where do we go after 7s? Follow this all the way here to 5f. It seems like a weird order, but that is in terms of energy. 5f has more energy than 7s. So s orbitals are low energy. So we have 88. That means we have 4 more to put into this f orbital. For the orbital configuration, we'll draw 7 lines because it's f. 1, 2, 3, 4, 5, 6, 7, and 4 electrons. They will all be unpaired. 2, 3, and 4. Like I said, if this is really confusing, hopefully the more you practice it, you'll get a little bit better at it. I'll give you a couple of example problems below But if you need help with this, please contact me.